Hello, nice to see you guys.
Good afternoon.
Doing?
We are fine. How about you?
I'm doing okay too. So looking forward for spring break. Hello. Good afternoon. So last time we introduced the concept of inductance and also considered it as in the scope of this element of electric circuit called inductor, which actually considered to represent all inductance of electrical circuit accumulated in this circuit element. So if we can say that electrical resistance is the measure of opposition to electrical current given circuit, then inductance is measure of opposition to the change of electrical current, and it always like, the effect of associated effect of self-induction always opposes any changes in magnetic field flux through the electrical circuit, and that's why inductance is such a measure which like quantitative measure of the opposition to the change of electrical current in electrical circuits. So today we continue our discussion of magnetic field energy. So this will be focused specifically on how is it possible to represent in terms of inductance and electric current energy of magnetic field. And also we will discuss LC, electric circuit, like oscillations in LC electric circuit. So it means electric circuit which consists of an inductor and capacitor with zero electrical resistance. Let me switch to our slides. And last time, as you remember, we considered RL electric circuits and resistor inductor. So if we have electric battery, electrical resistor and inductor in electrical circuit, then the energy which is provided to electric circuit from electrical battery, we can express it by the product of electric current and electromotive force of the battery, will split in two components. One will dissipate in form of heat over a resistor, and another will be kind of accumulated in the inductor in form of magnetic energy. So we actually, it was like previous, from previous discussion, we considered that electromotive force splits in two components, this voltage drop over resistor and voltage drop over inductor. So what we did now, we just multiplied left and right side by current in order to get electrical power. So there is, so we can say that some energy as a function of time is stored in inductor and the derivative of this function u, first derivative over time, can be represented as actually power. So it will be change of energy per time. So per unit time means that will be power, which will be accumulated in inductor because of this electric current flowing through this electric circuit. So that will be inductance L times I current times first derivative of electric current over time. So from here, we can write that du will be equal to L times I di. And when we want to get the total amount of energy accumulated in the inductor at some current I, we need to integrate this expression. So we go U, total energy accumulated in inductor, will be integral from 0 to L, sorry, not to L, to I. It's actually that current at which we want to know the accumulated energy inside the inductor. Integral from 0 to I, L times I times di. Obviously, inductance is a constant parameter. It does not depend on current. So we can, it's determined by geometric features of current distribution, as we know. So we can take it out from the integral. Here will be integral from 0 to I of I times di. So eventually we can write that it will be equal to 1/2 times L times I squared. So this will be the energy accumulated in inductor in the form of magnetic field. If you recall electric field, which is kind of accumulated in electrical capacitor, we were writing that energy accumulated in electrical capacitor will be equal to 1/2 C capacitance of this capacitor times potential difference in second power between the plates of the capacitor. So in similar manner, energy can be accumulated also not only in form of electric field, but also in the form of magnetic field, and it will be expressed where inductance of the electrical circuit and electrical current flowing through this circuit. So now if we consider, for instance, a solenoid, which represents such current distribution when we have periodic like repeating turns of wire. So solenoid consists of many wire coils, one after another. So its inductance can be expressed as mu naught times n squared times V, which is the volume of inductor, cross section of the solenoid times its length. This small n, its number of turns per unit length. Then we also remember that magnetic field is inside solenoid is mu naught times n number of turns per unit length times electric current. We have already shown, like derived this equation for magnetic field inside solenoid. So now we can express electric current from this equation. Will be equal to magnitude of magnetic field divided by mu naught times n. And now substitute this equation and this equation into the equation for energy of magnetic field accumulated in inductor with inductance L. In this case, it will be, this particular case, we are talking about some solenoid. So this will be energy is equal to 1/2 mu naught n square times V. And here will be magnetic field inside solenoid divided by mu naught n in second power. So eventually we get magnetic field magnitude in second power divided by 2 mu naught times V. If we want to know the energy of magnetic field per unit volume, then we can divide it by volume. So let's write here this small UB, magnetic field energy per unit volume in solenoid will be expressed as B squared divided by 2 mu naught. Now let us check and consider one interesting example. When we have again RL circuit, then we have some stationary condition when electric current is equal to its maximum value. Let's call it I initial. So and it's constant, it's DC condition. And then let's assume that this current starts to decay while running in this RL circuit. So we already considered this case last time, and we derive equation for electric current as a function of time for such RL circuit or decaying current that was maximum value of electric current. In our case will be I initial times exponent minus R divided by L times T. So we see that it's exponential decaying function. Over time, electric current will exponentially decrease its magnitude. So we derived this equation previously. Now what we want to do, let us check what will be the power dissipated in form of heat over resistor R. So let's call du over dt, like change of energy per unit per time. That is our power, and that will be so we can consider this actually as change of energy of magnetic field which is accumulated in in the inductor L. Because if we have stationary condition and we have this current I initial flowing through the circuit, means that, as we discussed on the previous slide, there is certain magnetic field energy accumulated in the inductor of this electric circuit. When we turn, let this eliminate power supplies, which keeps this stationary condition of constant electric current in the circuit, then current continues to flow according to this exponentially decaying over time function. And this current flows not by itself. There is some driving force for that, and that is conversion of magnetic field energy accumulated in the inductor into heat dissipated over the resistor. So that's why the rate du over dt, like first derivative of this energy accumulated in the form of magnetic field, will just show how fast magnetic energy is transformed into heat energy, like into dissipated heat over this resistor R. So the power means the rate of energy dissipated per unit time over a resistor is known for us from previous discussions. It is electric current as a function of time in the second power times electrical resistance R. So we can now substitute here the full function for electric current versus time. So it will be I initial times exponent minus R over L times T. This will be in second power times resistance R. Eventually we get I initial second power times R times exponent minus 2 R over L times T. So now we have this rate at which magnetic field energy accumulated in the inductor decreases via heat dissipation over resistor R. Now, if we want to know the total energy, which will be in this manner dissipated, and eventually it will be total energy accumulated in the form of magnetic field in the inductor, because all energy will be eventually transformed into heat dissipated on resistor. So we can just integrate this equation in the time frame from 0 to infinity. So we are sure that over infinitely long period of time, all energy will be like magnetic field energy accumulated will be transformed into heat dissipated over resistor. So we have integral from 0 to infinity, electric current initial in second power times R times exponent minus 2R divided by L times T times dt. So here we can take out the parentheses. These constants will be I initial square times R integral from 0 to infinity exponent minus 2RL times t dt. And in order to integrate this, we need to modify the differential to make it the same as argument of exponential function. So for that purpose, we need to multiply this integral with L divided by 2R. Then we have integral from 0 to infinity exponent minus 2R divided by L times t. And here will be, instead of dt, it will be 2R divided by L t. So now we can easily integrate this, and it will be actually here should be the minus in order to have the same argument, because it should be with the sign the same. So we kind of multiply by this minus L divided by 2R. So here this minus I initial square times resistance R. Here is L divided by 2R. And after integration, we get exponent minus 2R divided by L times t from 0 to infinity for time. And that actually stands for minus I initial square times R times L divided by 2R. Here it will be for infinity, for infinitely large time, it will be 0, this exponent, because it's with sign minus. So if we have minus infinity power, we get 0. And if we have 0 instead of time, we actually get unity. So it will be 0 minus 1. And eventually, our result will be I initial square. So minus and minus will cancel, times R times L divided by 2R. So after canceling this R, we get the expression of total energy dissipated over a resistor during this decaying electric current, and that will be equal to 1/2 times L times I initial square, which is indeed expression which we previously derived for the energy of magnetic field accumulated in the inductor. So we can approach this in different ways. So we can either calculate directly, which is kind of more straightforward, derive this equation for magnetic field energy accumulated in inductor, or we can calculate the total energy dissipated on resistor in RL circuit when electric current decays over time. For that purpose, of course, we need to know this time dependence of electric current, but we do know it, we derived it previously, so when we used it and calculated total energy from 0 to infinitely large interval of time, we indeed see that this energy will be equal to the energy of magnetic field accumulated in the inductor. So at this point, we can make a transition to our consideration of oscillations in LC circuits. And it can be shown like this. We have a capacitor, have inductor, and let's say we have some switch S. So this is plus minus capacitance and inductance. Let's consider that at some initial moment of time, we have fully charged capacitor, BQ maximum, are accumulated on the plates of the capacitor, and this switch is open, so we kind of turn it on at t equals to 0. So what will happen? It actually will be good to share my screen so you have better visualization of these processes. Let me share screen with you. Yeah, so this is the case. We start at moment of time t equals 0. It is fully charged capacitor and no current in the circuit. So when this capacitor starts to discharge, there is some current starts to flow through electric circuit. And at initial moment of time, all energy is accumulated in the capacitor. There is no, like in form of electric field, there is no magnetic field because no current. So when in the process of discharging, all charge is gone from the capacitor, electric current in the circuit reaches its maximum value. Means that the energy accumulated in the inductor in form of magnetic field also reaches its maximum value. So when it reaches maximum value, then electric current will continue to flow in the circuit and will charge capacitor, but with different polarity. So that's why we will see some transformation again of magnetic field energy into electric field energy. However, polarity will be different. And then again, after fully charging electrical this capacitor, there will be discharge of capacitor, and electric discharging current, associated discharging current will flow now in different direction as initially. So initially discharging because of plus minus polarity, it was going clockwise. Now polarity is minus plus, and discharging current will flow counterclockwise, and this accumulated energy will be transferred of electric field will be transformed again into energy of magnetic field accumulated in the inductor. So what is important here, that this process will continue kind of without any losses, because we don't have resistor here in this electric circuit, and there are no options to dissipate energy in form of heat. That's why we have always like 100% conversion of electric field into magnetic field and backwards. So this is very similar to the system which we considered in previous semester, a string mass system, when we have transformation between kinetic and potential energy, assuming that there is no friction, and that's why there is no dissipation of energy. So similar will be also for this LC circuit. Taking this into account, in any moment of time, there will be constant like total energy of the system. So either at t equals 0, we have total energy in form of electric field, then at some moment we have total energy in form of magnetic field. But let's say if you look here, when electric capacitor is not fully discharged and current hasn't yet reached its maximum value, we have both contributions to total energy from electric field and magnetic field. However, this total energy always remains constant. So if we come back to our slides, we can write that the total energy is equal to energy accumulated in a capacitor plus energy accumulated in the inductor will be equal to Q squared divided by 2C. This stands for energy accumulated in capacitor based on its accumulated electric charge, like at this given moment of time, and its capacitance. And also, oops, not, also plus 1/2 L times I squared. So also in this moment of time depends on electric current which flows through the circuit and inductance of the electrical circuit. So the fact that it remains constant can be shown if we take first derivative of this total energy over time. And any suggestions to what it should be equal in order to highlight that total energy is constant?
0.
0, yes. So first derivative should be equal to 0. And here we get the derivative of this function, which describes total energy, which we just have written here, plus 1/2 L times I squared. This will be equal to Q divided by C times dQ over dt plus L times I times di over dt. And this is equal to 0 here. So assuming that dq over dt, this is actually electric current because it's change of charge per unit time. Then we can write that di over dt, the first derivative over time of electric current, is the second derivative of electric charge over time. So taking this into account, we can write that Q So this expression will be equal to Q divided by C plus L times D square Q over dt square. And this is equal to 0. So from here, d square Q dt square is equal to minus 1 over LC times Q. So this is second order differential equation, which is very similar to equation for the vibrating spring mass system. So that was d square x over dt square equal minus k divided by m times x. So k is the spring constant and mass is the mass of the block. So in this case, like for mass spring, we were solving for position of the block. In our case now, we solve for electric charge as a function of time. However, these equations look identical, and obviously we will get the solution for this second order differential equation similar to the position of the spring block system. So if we go to the next slide, let us write the form of solution for this differential equation. So Q as a function of time will be equal to Q maximum times cosinus omega t plus phi, some phase initial phase shift, and this omega angular frequency for the oscillations in LC circuit will be equal to 1 over square root of the product L times C, so-called natural frequency of oscillations in LC circuit. So now if we want to know how current will change with time, we need to take first derivative over time of this function Q versus time. It will be dq over dt. That will be minus omega times Q maximum sinus omega t plus some phase shift phi. So if we assume in our case that at moment t equals 0, electric current is equal to 0, and Q is equal to Q maximum. That's what we considered at the beginning. Then we can substitute, like for instance, taking into account this equation and considering t equals 0. So current should be also equal 0. So 0 is equal to minus omega times Q maximum sinus phi. And since these two guys are not equal to 0, sinus phi should be equal to 0, so we can consider phi as also equal to 0. So eventually we can write for electric current as a function of time. That is Q maximum times cosinus omega t, and electric charge as a function of time, and electric current as a function of time is equal to minus omega Q maximum times sinus omega t. Or we can write, instead of these two terms, just I maximum. It will be minus I maximum times sinus omega t. So we have these equations which describe time dependence of electric current and electric charge. Now we also can come back to the discussion of energy accumulated in capacitor and inductor. So UC plus UL. So as function of time. So maybe let me specify it here. U as a function of time. So we can write for electric field energy Q maximum square divided by 2 times C cosinus square times omega t plus energy accumulated in inductor will be 1/2 times L times I square, and we substitute instead of I also this time dependence of electric current. I maximum square times sinus square omega t. So we know that there is no dissipation of energy, and that's why maximum energy accumulated in capacitor is equal to maximum energy accumulated in the inductor. Thus, we can just take out the parentheses Q maximum square divided by 2C, considering that this is equal to Q maximum square divided by 2C. And eventually we will get, here, so this will be equal to Q maximum square divided by 2C. And here it will be cosinus square and omega t plus sinus square omega t. And this guy, like the expression in the parentheses, is equal to unity. So the total energy over time will not change, because at any moment of time it will be equal to the it will be constant and equal to initial energy, let's say, accumulated in the capacitor before this time moment t equals 0, when these oscillations in the LC circuit started. So that is another proof of the fact that total energy remains constant and does not change with time. So if you have any questions, you're welcome. We introduced today expressions for the energy of magnetic field and calculated it based on the initially derived it based on the RL electric circuit consideration in the form of also derived it in the form of heat dissipation over resistor when we transform completely energy of accumulated in the inductor into heat dissipated over resistor. So it gave us also the same expression for the energy accumulated in this inductor, and also considered LC oscillations. That's kind of important topic because LC circuits are quite often used in electrical circuits for fine-tuning of different like frequencies and in radio electronics in order to receive some signals and amplify them. We have shown that in the absence of electrical resistance in such circuits, total energy remains constant, and we have only periodic transformation of electric field energy into magnetic field energy back and forth, and also derive equations for time dependence of electric charge at the plates of the capacitor and of electric current flowing through such LC circuit. Eventually, we have shown that indeed over time, total energy, the sum of energy accumulated in the capacitor and inductor, doesn't change over time and remains constant, equal to the initial energy accumulated in the capacitor prior to the start of these electrical oscillations in the LC circuit. Then with this, I think we finish our discussion today. I wish you good spring break, get some energy, rest from this everyday studying experience a bit, and with new energy and excitement, start the second half of semester. Take care and stay healthy and safe, and enjoy your spring break.
Thank you very much, Professor. Excuse me, I have a question.
Yes.
Do you know about the date and the mode of our final exam?
Well, final exam. I'm not sure right now that we already know the exact date for final exam. I believe there were some suggestions, but we will know it probably a bit later.
And what about the mode? Is it going to be online or offline?
Yes, it will be online. It will be the same, like this same procedure we along Kappa as our midterms.
Okay, thank you very much.
You're welcome.
Thank you for this lecture. Have a nice break time too.
Yeah, thank you. You too. Take care.
Have a nice weekend. Thank you. Goodbye.
Mm-hmm.